phased array ultrasonic inspection technology in automotive manufacturing. So I hope today that I can educate everybody on ultrasound inspection. So we'll go into some detail here. So first, ultrasonic spot weld inspection is a non-destructive testing method that's used to evaluate the quality and integrity of spot welds in various industries, including automotive, aerospace, and manufacturing.
The next generation.
UT can be used if a component is to be inspected 100% for nugget size, internal material defects, surface cracks, or wall thickness measurement. UT can also be used to inspect components post-welding process in a weld inspection station or offline. UT technology uses a frequency range of 0.5 to 50 megahertz, but for spot welding, inspection is typically 12 to 20 megahertz. The sound refers to the vibration of molecules, and in contrast to light waves, etc., it's bound to matter. Ultrasound is transported in the form of mechanical sound waves. The quality assurance of spot welds is extremely important for the functionality and safety of the parts. Resistant spot welding can be inspected in various ways. Peel test, which is a tearing of the weld nugget. Use vernier calipers to measure the X and Y direction. Add the two values and divide by 2. Chisel test, which is performed to drive a chisel to see if the weld holds. Cross-section analysis, this is where you do cut the weld and use etch and polish technique, and then under a micrograph you can inspect the cross-section. Strength, this is where you can measure the physical tensile strength of a weld. And then finally, ultrasound. So the major benefits of UT testing is that it has a very quick inspection time, consistent measurements, it does not damage the parts, the labor safety issues to destruct the parts is avoided, and UT does not require a separate sound barrier booth for destruction. UT requires a coupling gel that transfers the ultrasound into the material and fills in the indentation of each spot weld. Coupling is comprised of a propylene glycol and water. So what are the materials for spot welding ultrasound inspection? Coated and uncoated steels, low to ultra strength steels, stainless steel, and rolled and cast aluminum, and also welded to each other. Stack-ups for inspection are 2 and 3 thickness joints. The thickness ranges for one sheet is 0.60 to 5 millimeters. So UT uses high-frequency sound waves through the sheet metal, spot weld, and the heat-affected zone areas. During the inspection, ultrasound waves are sent through the spot welds using a specialized probe. These waves penetrate the material and reflect back when they encounter a change in density, such as a weld or a defect. The reflected waves are then detected by the same probe and analyzed by a computer to create an image of the weld. Resistant spot welds can be evaluated by the UT echo positions on a time scale and their attenuation characteristics. So Vogt utilizes phased array technology, which is an electronically scanned array. It uses a computer array of antennas, which creates a beam of ultrasonic waves. Phased array technology offers several advantages, including improved resolution, electronic steering, and focusing of the beam. It also has the ability to track multiple targets simultaneously.
So now it's my turn to explain a bit about phased array technology. We start with the conventional technology. There, you have a probe which has the same size as the minimum diameter which you like to achieve with your welding. So if you want to weld minimum 4.5 millimeter, you choose a probe of 4.5. If you want to have 7, you choose a probe of 7. So there's a bunch of diameters from 3.2 up to 8, 9 millimeters of probes. So the operator runs around with this pocket full of probes if he has to test a lot of different thicknesses and different minimum diameters. By this minimum diameter, we achieve, if the spot is big enough, that we only get the signals from the back wall. So clear back wall echo reflection without any reflections from the interface. So that's the conventional technology. Now, time has changed and we are in imaging systems. These imaging systems normally use multiple elements, 52, 64, depends on the instrument. We use 121 elements, which is much more. But we will do much more on this on top. We will have 729 A-scans sampled on each spot array. We use for this the 11 by 11 elements as a square, and we combine these small elements, which have a size of 1 millimeter, we combine these to a virtual probe. And that's what phased array technology is doing. Phased array technology is producing a lot of virtual probes running around in your matrix or a longitudinal probe if you use it for weld inspection in other areas. So the matrix probe, which you see here on the left side, the matrix probe by 11 elements. We take, in our case, 9 elements, put them together, and we get one probe with a diameter of 1 millimeter. And by that, we create ultrasonic signals. We run through the whole matrix, like you see here, with all these elements combined together, and these elements doing two things. First, they shoot at the same time, or quite a bit delayed each element. In case we delay the element electronically, we have a steering of the beam. We use the steering of the beam as an electronic steering, and also what we can do is we can focus with this probe. So we focus on the surface or on the interface echo or interface plate. So by this steering and focusing, we add more physical tests. And there we get to a grid which you see in the middle. A grid. Oh, sorry. Okay. So you see here from the grid of 1 by 1 millimeter, by using steering and focusing, we get to a resolution of not 1 by 1, but 0.33 by 0.33, which is indeed 0.01 square millimeter. This is our resolution to measure the diameter of a spot. And then the software, which we add to the system, evaluates if the spot is good and not good. Nobody can look on 729 A-scans. It's too much to evaluate by manual checking. So the software must be good enough to evaluate with all the processes and things happening in the spot. On the A-scan, we see the same as in the manual testing. All the signals are the same as in the manual testing because it's physics and ultrasound. So we get the ultrasonic signals from the backwall echo, as you see here, from the spot. On the y-axis, you see the amplitude, which is the power which comes back from the backwall. And it drops down by the multiple echoes running through the spot. So on each surface and the backwall of the spot, you get reflection. And the ultrasound is running inside the spot a lot of times, much more than you see here, because we stop the width of the screen by a certain millimeter. We don't need more signals. But it's running all the way. And at the end, it's giving a very little bit to the air on the back wall, but most coming back to the probe. So each time, each cycle, when it goes down, it is reflected on the back wall, going up is reflected on the surface, going down in the spot, but a part goes back into the probe. And this gives us the multiple echoes. And this is seen on the screen. So here you see the beam is running all around. It's not like here shown one underneath the other, it's on the same line. But to show it to you, we put it underneath. So beam is going into the spot, running inside the spot, always getting apart back to the probe, and then we get these echoes which are dropping down. And they're dropping down, this attenuation happens because the grain always is patterned the ultrasound somewhere, not back to the probe. Which is indeed a signal which we use, because when the grain is very big, you have a lot of reflections inside the grain, and you get less signals back. So the attenuation is much more dropping down than on a spot which is not welded. So a good spot looks like this. You get the surface echo, which is, sorry, too fast. This was a lot of strokes. There we are. Okay. So you have the surface echo from here, the back wall echoes with a certain distance of about, I don't know, 2.5 millimeters. No intermediate signals. Going to a small spot, you get intermediate signals at the area of the first layer. So very simple, if there are intermediate signals which are in the range of the first layer, very easy to understand that this is a bad spot. Too small spot in that case. Or you have stick welds, which sometimes are very difficult to test. Stick welds, you see it, go back. Stick welds here have in the area of the first plate, they have no signals. Sometimes they look completely like a back wall of a good spot. And their only attenuation might be the right one to evaluate these spots. So in our software we have a peak detector. We are not working with gates, we are not working with areas where we expect something. We have a peak detector, like a pattern recognition, running all through the A-scan 729 and checking all the peaks which have a maximum. And then finding out the cycles and the relations of these different signals to each other, and the evaluation process gives you the result. So these kind of signals which you see here, good spot, small spot, stick spot, need to be evaluated in the past by the guy having a manual hand testing instrument. In the future now with the imaging system and software, this has been done by the system itself, by the product itself, by phases in this time. So I hand over.
So now talking about the Phasis Neo products. Phasis Neo is the manual handheld system, and Phasis Blue is the robotic inspection. We're going to talk about that a little bit later. So with the manual or the robot, you have a phase array probe. It comes in 2 meters or 5 meter cable lengths. You also have a remote control which allows the operator to accept the weld or retry. You have coupling gel. You also have different delay lines that are used here, depending on the product, flange width, and any interferences. And there's also a calibration block here. We'll have some units here that you guys can practice on, but the calibration block is used for the operators to just measure 4 welds at the beginning of the day to make sure the system is running correctly. So part of an operator's task is to run a test plan. It's sometimes called a part routine or a scan plan. So what's typically done is a weld graphic is copied into the machine, the software, and then you assign the spots according to the sequence you want the operators to measure. So each unique weld ID is set in the test plan, and then it's shown in green for the operator. As they measure each weld, it'll automatically advance to the next spot. So So when an operator goes to measure a specific spot, they get what's called a live C-scan, which is the measurement for positioning and vertical focusing of the probe on the surface of the spot weld. You also get the live A-scan echo readings underneath. Once the operator hits record, you get a D-scan, which is a time of flight C-scan, result of the spot weld. The measured nugget diameter is compared then to the target nugget diameter that you're trying to achieve. You get a real-time result notification. So in this example, this was a small weld nugget. So this was recorded under the target, and then instantly it will be a small nugget. If the operator records this, this will